The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Good morning. I have 8:30, a little bit after. I want to welcome you to the session on design and construction of concrete tanks for refrigerated liquefied gas containment, RLG for short. And engineers will always like these acronyms. But I'm Charles Hanscat. I'm incoming chair of ACI 376. I'm going to give you a little bit of an introduction to the concrete refrigerated liquefied gas tanks and our code, give you an idea of the regulatory situation that covers these tanks. I've been involved with ACI since about 1981. I don't believe it's been that long, but somehow it has been. Been very active in all the ACI work that deals with concrete liquid containing structures. So I'm a past chair of ACI 350. I've also been very active with our committees that deal with 371, 372, and 373 that deal with pre-stressed concrete tanks. Additionally, I've been on the board with TAC, and I'm one of those that just hasn't learned how to say no, apparently. I'll give you an overview. I'm going to talk in my presentation about the history of concrete structures and refrigerated liquefied gas, RLG. Why we need a code. Give you an idea of the committee, ACI 376, how we put the committee together, what kind of representation we had. Give you an outline of the document, the areas that we cover, and the current status. How many here have seen the ACI 376 code, the provisional code? Mostly committee members. And so we'll give you some of the details of that as we go along. This is the title. It's certainly a mouthful. It's the code requirements for design and construction. This is a very unusual code for ACI. You'll see 318 it's about design. 301 is about the construction side. We actually kind of have both together. And this is a different creature for ACI because in our marketplace for LNG tanks, it's pretty much done in design build format where it's turnkey. So an owner puts out a specification, a requirement, scope of the project, and then the design build team actually does the design and construction of the structure. This is listed as 37610. It was finished in 10, it was provisional. The final will be coming out, and I'll go a little bit into detail later. But it's a complete standalone code and commentary. Those of you in the nuclear industry might be familiar with ACI 349. 349 is a dependent code. You have everything that's different, but you don't have anything that's in 318 that's the same. So ours is different. Everything that relates to the tank design and construction is actually in our code document. And we have commentary that helps to explain the code sections. We are in the title RLG, but in actuality, the majority of the tanks, the big tanks that are going in, are liquefied natural gas, LNG. So talking about LNG, it's a clear, colorless liquid, lighter than water, boils at a very warm minus 260 F at atmospheric pressure. One of the interesting things, it expands 620 times when it goes from the liquid phase to the gas phase. So that's a huge expansion when it evaporates. Essentially all methane, and the liquefaction strips most of the higher freezing point products away from the material. Where are LNG tanks used? This may be an offshore platform. You come in, you have a liquefaction plant, and then storage before it goes to a ship to take it to where it can ultimately be used. Alternately, you might have a ship come in, there's a terminal facility, storage, local storage before it's gasified, taken out into the system. That's an import scenario. In an export scenario, you may actually be producing natural gas out here, come in, liquefy it, store it in the tank before it gets put on the ship to go somewhere else in the world. The first LNG pre-stressed concrete tank was built, it was a 950 cubic meter liquid oxygen tank in East Chicago, Indiana, about 250,000 gallons if you do the conversion, built by the Preload Company in 1953. So there's a pretty long track record of these. It was built by the Preload Company, Preload Incorporated. And any of you who've been involved in the industry, this is really the first push of concrete into this marketplace. Jack Klausner and Nick Lagatos. Jack has passed away, but Nick is still active with Preload. Were some of the founding fathers of use of pre-stressed concrete tanks for storage of RLG. And here's a tank today. You can see, give you an idea of the perspective. Here's a gentleman standing down close to the tank. So we're talking very tall tanks. This one's externally post-tension. You can see the buttresses, then a dome cover for the tank. But these are very, very large structures. We're talking storages that go up to roughly 20 to 25 million gallons of storage in a particular tank. We're talking about full containment LNG tanks. To give you an idea of what this one actually has, the inner containment, the outer containment, we have insulation, and there's an inner shell. And so the material that's actually exposed to the LNG or RLG is a 9% nickel steel or pre-stressed concrete. We have a single containment, which basically that's the containment of the wall. It's insulation, it's the vapor barrier. The single containment would have to have a berm or a concrete or pre-stressed concrete berm, that if there was a failure of the primary containment, this berm would actually contain the liquid on site, so you don't have it running all over the countryside. Double containment, what we've done here, we basically take that outer berm where we built a big wall adjacent or very close to the primary containment, and it serves, if there's a failure or rupture of the primary containment, the secondary will maintain the liquid on site. And then a full containment, very similar. Really the big difference, what's the big difference between double containment and full containment? The roof is actually attached to the outer containment, so our vapor containment actually happens in the full containment out of the secondary containment wall. This is an old slide. I didn't find a new one, but this gives you an idea of existing proposed North American LNG terminals. So quite a few around. Placing in terminals, but not in my backyard, has been a problem. I think one of the things, one of them listed up here is Long Beach, California. Chances of that are probably nil, but are very close to nil. But, you know, there's a lot of potential out there. As energy prices rise, when gas is $5 a gallon, and natural gas is still a very economical energy source, you know, the economics may drive the U.S. and the rest of the world. We're talking, this is the U.S., but there's a lot of facilities going in worldwide. What's the current practice? Currently, LNG tank containments, predominantly the 9% nickel steel. There's 5083 aluminum is listed, but really not used. Stainless steel, inbar steel, could be considered, but very expensive, so it's not really practical. Both the metals are extremely tough at the surface temperature. You have to think that you're dealing with the steel being exposed at minus 260. That's a very critical situation for steel. The outlet vessels nowadays are usually carbon, though we're starting to get an introduction into the marketplace, and we'll show the photographs in the second session about construction that we're doing now with concrete. And the diking or product spillage, I talked before about the berms. There have been earthen berms, or there have been concrete berms, pre-stressed concrete proposed for containment. Give you an idea of what's the history of concrete in LNG. I mentioned the first was 1953, but there was actually a tank in 1952, kind of a test tank that was done. Precast line concrete tanks, these are predominantly the preload design. I mentioned preload before. You have in Barcelona, 2 tanks in 69. You can see the list here. 2 in Philadelphia, 74. We've got Staten Island, this is an interesting one. 2 were constructed and near completion or fully completed, very large tanks. And because of its proximity to New York and I think it may not be the Hudson River, but it's one of the rivers around New York. It was decided that they would not put them in service because it was a risk that if there was a failure, there was just too much exposure in the surrounding communities. Kind of not my backyard problem. Give you an idea of what are we talking about in terms of volume. I do a lot of water, wastewater, industrial process, so I deal with gallons. But if you look at Barcelona, 80,000 cubic meters, that's 21 million gallons of storage. Very, very large containments. A lot of this liquid in one place. Concrete advantage, comparatively robust. You look at the thickness, the stiffness of concrete versus steel. That's a big plus. Concrete automatically provides corrosion resistance and fire protection to the tank structure. And it's more resistant to fire, explosions. Terrorist actions have been a consideration. And it's not just after 9/11. This was, to some extent, a consideration earlier on. The metal shell, what do we look at when we talk about the metal shell? They're very efficient for containing liquids. You get, with a cylindrical shape, a very thin shell that's required. But, and the cost of steel, the thinner you can make it, the higher the strength of the steel, the better you're going to be in terms of the cost of the project. But you have corrosion protection problems with the exposures, not only to the contained liquid, but to the external environment. These are built along the seashore, a saltwater type exposure, a lot of potential problems with corrosion. And the thinness, you don't have the robustness that you have in concrete. And what's the regulatory situation? You have DOT, which has rules for LNG facilities. This is the provision that deals with pipelines, 192. 193 is the one for LNG facilities. And then there's NFPA, National Fire Protection Association, 59A, and it's the current standard which governs the LNG industry. So here, just to give you graphically, we have the DOT has regulations that refer to NFPA 59A. 59A is titled Standard of Production, Storage, and Handling of LNG. It's also referenced by FERC and other agencies, and it's really used worldwide. We talk about it, we're thinking in some ways in most of our ACI documents about local things happening in the U.S. and Canada, but this is really a product that's used worldwide, and the 376 code will be something that's applied worldwide. What's in NFPA 59? These are all the things. I'm not going to read those off because this is the one we're really interested in, the stationary LNG storage containers. What's right now, the current NFPA 59A is a 2009 edition. It, for steel tanks, uses API 620, which is a design construction of low pressure storage tanks. And then for concrete, reinforced concrete or pre-stressed concrete, it uses 318, which that's great, that's a code, but that's a code for buildings. It doesn't deal with a lot of the durability and leakage, crack control issues that would be important for a liquid containing storage. They also reference 372, 373. 372 is a wrapped pre-stressed concrete, circular wrapped pre-stressed concrete tank report. It's not a standard, it's not mandatory. They also reference 373, which is internal tender. NFPA 59A, the next version, which will be in 2013, I think will be the actual number. It's very close to completion. Will actually now refer directly to ACI 376, and it refers still to 620 for steel. In the interim, API has put together a standard 625 that's tank systems for RLG storage that deals with both steel and concrete, but they recognize that their expertise was really not in the concrete world, so whenever they refer to concrete, they have actually referred back to ACI 376. So our code's being referred to in API 625. So why would we have a reason to develop a code? First thing, give the industry a mandatory document that can be referred to in these regulatory documents. NFPA 59A can make a direct reference to 376. It doesn't have to say 318 with these changes and 372 and 373, which were not mandatory documents. Really focuses everything in our 376 code. And it makes for concrete and LNG tanks that are, as I've mentioned before, more robust, more resistance to fire and terrorist activity resistance. So what's the history? In February of 2003, NFPA actually approached ACI and said, hey, can you guys think about developing a code? We're using 318, 372, 373, but it's really awkward. What can you do? So in 2003, in August, we put together some interested parties. We had a little meeting, I think it was in Washington, D.C., to talk about formulation of the committee. The committee was actually formed in June of 2004. We had our first meeting of the code committee in October of 2004. And it took about 5 years to get it to where it could go to TAC. Those of you committee members know what a challenge that is. Because then January 2009 to February 2010, that was what it took us to get our TAC review, get the response to TAC comments, and then release of a provisional code. At the end of the provisional code, we put it out for public comment, and those have been reviewed, responded to, and the final version should be coming out spring this year. And I think today is the first day of spring, so we have about 3 months. Maybe that'll work. Depends on the publication department at ACI. What's the objective? Use reinforced pre-stressed concrete tanks for primary and secondary containments. We're going to deal with all the members that are part of these two systems. Who are the people? We have, you can see the list. We have engineers, contractors, owners, and it's not just in the U.S., it's from around the world. We're getting experience on these types of tanks from everybody who's been involved in the industry. And what's in our 376 code? First part, we cover materials and tests, and this is really just an outline of what you're going to hear today and the rest of our sessions. I'm just giving you an overview, and you're going to have individual speakers deal with each of these sections as we go along. Design loads. Remember it's design and construction. So we have some minimum performance criteria that we're putting into this that deals with the different containers, the primary, secondary containers, roof, fatigue, load factors, strength reduction factors. We always have to complicate the design for those kinds of things. Analysis and design, which foundation, roof design, as well as the container design. So we're really dealing with the total project, the total tank, what it takes to get it in place. Detailing of reinforcing. The pre-stressing is a form of reinforcing, the concrete containment and anchorages, liners and coatings. We cover foundations. You can imagine, minus 260 F, there's a little bit of, there can be some things going on with the geotech. So foundations were important to us. And we're not saying we're geotechnical engineers, but we do give some general guidance on what's required for developing a design of an LNG tank, considering the foundation. Construction requirements. This isn't a spec. It's not like you will see necessarily in a 301 that you can just hand to a contractor, but it's guidance to the contractor. And we're talking about things like tolerances, shotcrete. Shotcrete's not addressed in 318, but we do cover it. Pre-stressing, forming, joints. And then commissioning. I mean, this is a little bit unusual too, because this is actually startup and in some ways maintenance of your facility. You can see here the fill methods, decommissioning, the cool down, getting ready for introducing the low temperature liquids. A lot of things that are really unique to LNG tanks. And then we have an appendix that has some of the details, so you can see this is what it looks like generally. We do have an appendix that deals with offshore concrete terminals, so we'll be developing in our next revision a little bit more on that. And then fatigue performance. It's a code and commentary, so we're thinking that ultimately it may look like this, which is the code. For those who use 318 or 350, you've got the code on one side and commentary on the other, and they're lined up. If you go into the provisional, unfortunately, not unfortunately, it's all there, but you'll see here's a code provision, and then there's the R as the commentary. So they're in line, they're close to each other, but it's not the side-by-side that you saw in the 318 or 350 document. And in the final printing, I think it may actually go side-by-side, but I'm not sure. It's going to be dependent on what the ACI, the publishing department, wants to do with it. And for those of you who go online, here's some links. You can take off the slide that'll give you access to some information. Really, you can do a Google search that pulls up a wealth of information out there and give you this first one, or not the first one, this last one is a pretty good primer. So I would caution you to get into it. Some of their conversion factors don't match what I see as being the right conversion factors, but it gives you a good primer on LNG, and so I just offer that caution. And I thank you for your time. We've got about 3 minutes for questions,